Now, can you hear me?
Yeah, now.
Yeah, because we were off in the.
Okay.
Yeah, okay.
Yeah,
Sure,
they
okay.
do. Yeah.
Perfect. So I'm sharing, right?
No, you're not.
Yeah, you are sharing the screen.
Oh, yeah, okay.
Yeah, we can see the screen now.
Great. So I share again full screen. Yes, perfect. Thank you for taking this. So I was saying that we don't need to go to the super-Eddington regime to really see that the accretion can be remarkably complex. So in our work in 2024, we showed how hydrogen column density from dedicated X-ray observations vary from orbit to orbit significantly compared to the average trend from MAXI, that is our sky X-ray monitor. But how bright can accretion be? And since already Roberta gave a nice talk on super-Eddington regime and pulsating ULXs, I will go more straight to the science. When matter falls onto the compact object, gravitational energy is released and converted into radiation. Under these simplifying assumptions, that is spherical radiation, spherical symmetry, and isotropic radiation, the outward radiation pressure can eventually balance the inward pull of gravity. This is where we define the Eddington limit and is often treated as the maximum steady luminosity an accretion system can sustain. And with this, we define the mass accretion rate, m dot, equals to Eddington luminosity over eta times c squared, where eta is the radiative efficiency of the radiation. So those instances with an m dot greater than the super of the m dot Eddington, they are called super-Eddington. However, what it is important is that accretion doesn't happen in spherical conditions. When in falling material, the infalling material carries angular momentum, and a disk is formed, allowing radiation to escape perpendicular to the inflow. Ultraluminous X-ray sources are our window to super-Eddington accretion. Usually, the main observable is luminosity, but luminosity is not always a direct tracer of accretion. Pulsating ULXs are in this context important because the neutron star spin evolution provide an independent measurement of the accretion rate through angular momentum transfer. Therefore, using pulsating ULXs allow to test whether luminosity is a tracer of mass accretion rate. In P13, coherent pulsations were detected around 10 years ago, and only a handful of pulsating ULXs have been confirmed to date among the whole population of ULXs, although the exact number of confirmed pulsating ULXs really depend on how strictly you define the term confirmed. In the next slides, I will focus on P13, for which we have more than 40 XMM Newton and NuSTAR observations. We also have swift monitoring of the source, which is shown in this upper panel. And we have XMM Newton in blue, NuSTAR in yellow, and the red markers are the epochs where we have simultaneous coverage from both instruments. I want to highlight the total luminosity light curve here. It decreases to when it arrives to 2020, when it reaches the lowest luminosity, and then recover again the total luminosity that it has before. So this raises the central question of the talk that I want to answer, that is, what is causing this change in total luminosity? Is it intrinsic, tracing the accretion rate, or is it primarily geometrical? And I also want to highlight this data point here because in a few slides I will speculate where we have here a cycle that is around 8 years in the geometrical interpretation of the precession of the disk. But first of all, let's understand what the P13 spectrum traces. In ULXs, it traces physical regions. We have the optically thick part, the inner regions, and the regions closer to the neutron star. Those physical regions doesn't necessarily correspond to separate model components. And in early ULX studies, they were modeled with only 2 phenomenological components. For P13, Don Walton and collaborators in 2018 showed that a third component for P13 is needed to model the hard pulse emission. Therefore, in our work, we adopt a DSBB, blackbody, and cutoff power law description. For the softer thermal component, we use a multicolor disk rather than a more complex descriptions like a slim disk with a free radial temperature profile, because the data doesn't require that complexity, because the high energy curvature is already accounted with the blackbody and the cutoff power law. The first result is the general drop of flux in all the thermal components, the soft, the hotter one, and also the high energy tail. So that means that the big changes that we observe affect to all spectral components at the same time, rather than having one of them dominating. And also important, the offstate, we defined it, that I forgot to mention before. We define the offstate as those epochs where we don't have pulsations, okay? So we are not able to detect pulsations. So we also look at the flux and temperature relation of the soft and hotter thermal components. The data deviate from the T to the 4 scaling from the standard Shakura-Suniev disk, and the two temperatures stay at a nearly constant temperature, besides the large flux variation of more than 1 order of magnitude. But flux scaling is not enough to explain the offstates. What I show in this figure is the offstate spectrum fitted with the onstate model. The onstate is fixed, only allowing a multiplicative constant to account for the difference in flux. The onstate is obtained from one of the epochs that we have a broadband coverage, so the model is less constrained. And if the offstate were simply a fainter version of the onstate, we would expect the residual to distribute around unity across the full energy range. Instead, we have this energy-dependent residual structure below 1 kV, which means that the spectral shape during the offstate is varying. Although the main factor that drives the offstate is the suppression of flux, we have a mild change of the spectral shape. And this spectral shape is better seen when we look at the model components of the onstate and the offstate. The first interesting result is that they don't drop at the same amount. So the thermal components, they drop by a factor of 30, and the high energy cutoff power law, it drops around 50 to 80, a factor of 50 to 80. And regarding the temperature, the soft thermal component drops by a factor of 30, whereas the hotter thermal components only at 10%. So during the offstate, there is a progressively decrease of the DSBB temperature. And this can be seen here, right? If in these arrows that I draw, from the peak of the onstate, it doesn't go to the peak in the offstate. It is shifted towards a lower energy. And this is about right if we do a small calculation, that is the soft thermal temperature is around 0.3 kV. So that corresponds to a factor of 3 in energy. So the peak is around 1 kV, and it makes sense. And the same with the blackbody. We also looked at timing analysis. So here we calculated the pulse fraction. The pulse profile of P13 is, it doesn't seem to change from observation to observation. And this simple mathematical description is sufficient to describe the pulse fraction. The first result here is the energy dependent of the pulse fraction with the energy. So the higher the pulse fraction, the higher the energy. And this makes sense. This is what we expect, right? Because if I go back to this slide, there is a cutoff power law contribution, that is the model component that is expected to be tracing the pulse emission, also contributing to the soft emission, although the main contribution is at high energies. The interesting part here, though, is this decrease of the hard band pulse fraction of the XMM observations prior the offstate, whereas the soft band pulse fractions remain approximately constant. This is what I just said. And also we checked the correlation of the pulse fraction with flux, and we found a moderate anti-correlation, which means that we explain as a contribution of the thermal components via dilution to the total pulse emission. And we continue to monitoring the spin of the source, and it seems to continue spinning up faster. So we try to feed a paraboloid, one single linear feed, but the best solution is the 3-segment spin solution. And after the off state, the neutron star seems to rotate 50% faster than before. The proposed geometry that I'm going to discuss now, it's the long-term average picture of the source. That is, it can be that some observations differ from the picture I'm going to describe now. So we have the cutoff power law produced closer to the neutron star, tracing the accretion column. The black body, that's the optically thick plasma outside the magnetosphere, as discussed in the many papers of Mustokov, and in the base of the funnel. And we have the DSPP that comes from larger, more extended areas of the super-Eddington flow. So if I put everything together, the on state versus the off state, what is the change in view and angle? So with the on state, we look all the way down the funnel along the funnel axis, whereas in the off state, we transition towards angle where we stop seeing the inner part of the disk. And this explains the suppression of flux, the total flux. Also, why the cutoff power law decreases more than the thermal components, the decrease prior the off state of the high energy pulse fraction, and what happened with this DSPP temperature, why it decreases in the off state. So we explain that as increase of the projected area of the DSPP. So as we go towards the off-state angle, we increase the cooler regions of that DSPP models. Therefore, the temperature decreases. So if this picture is correct, thank you. So if this picture is correct, first of all, we can speculate whether we will have another off-state, right? If you remember the point that I highlighted with the lowest flux in 2012, then off-state in 2020, so the next one would be around 2028, 2029. And secondly, if this geometrical explanation is also correct, we would expect to be able to measure outflows as an indication of this dynamic wind structure. And for that, we would need a NewAthena, a high-resolution spectroscopy, and Matteo already presented how ULXs NewAthena will be able to reveal winds in ULXs. In this last paper from Ciro Pinto, in a similar ULX, he showed how XIFU will be able to detect oxygen 7 and 8 lines that are associated with winds. And also I wanted to highlight this paper from Peter Kosek in 2021, because he stacked the RGS data from P13 and found a line at 20 Armstrong that correspond to oxygen 8, although with a low significance. I think it was 1.2. But together with our results, that is this energy-dependent structure, those all are hints that we might be able to detect outflows in P13 with the NewAthena XIFU. So that would be thanks to a larger effective area, and that means a larger mirror module. And since my main occupation during the last 4 or 5 years was the optics of NewAthena, in the next slides, I will walk you through a little bit of X-ray instrumentations for future missions, although I will not have a lot of time to cover everything, but I will be very happy to discuss this with you after the seminar. NewAthena larger effective area is possible thanks to silicon pro-optics technology that consists in very thin silicon plates that are stacked together in a stack, then assembled together into a mirror module, and we will have 500, 600 of them integrated in the telescope optics. The assembly of the mirror modules, this is me with the mirror module jig. We have a control of each single stack, 4 of them to assemble a mirror module, 6 degrees of freedoms per robot, we use X-ray illumination to bring them to nominal position before bonding. This process is very iterative in the development phase we are right now. And a lot of X-ray scans are needed. We need to check also with the database with our colleagues in the Netherlands to get information of the surface of the plates. So all requires a lot of data handling, and that was also one of my main occupations. The production of NewAthena is shared among different locations in Europe. We have BESI2, a synchrotron radiation facility in Berlin, where we assemble the mirrors. This is the interior of BESI. I like to describe this as very organized chaos because it seems very chaotic, but everything is in the place that it should be to work. And we have ALBA, is the synchrotron in Barcelona that we started operations around 2 years ago. And what you see in the picture is Minerva, is the third beamline that will participate in the building of the optics of NewAthena. It is way emptier because it is 20 years younger than BESI2. And we will use up to 5 beamlines for the mass production of NewAthena. Nowadays, we're investigating whether we can apply the same technology to build focusing optics in other energy ranges. In particular, change the physics we use. Instead of creating incident angles, we use diffraction in Laue geometry. So we make the X-rays go through the whole bulk of silicon to achieve focusing optics in the 82 to 100 kV band. And this is not just a conceptual work that we are doing. It is actually the architecture proposed for FENTO, that is a ESA M8 class mission led by Philippe Laurent. And as I said, I don't have more time to go into the details of these instrumentations, but I will be very happy to discuss them after the talk. So to conclude, I discussed the P13 variability that we observe as a warp process in a super-Eddington accretion flow, and it helps constrain the still largely unknown part of the inner accretion region. We will need NewAthena XIFU, high-resolution spectroscopy, to probe ULX outflows, but also X-ray polarimetry missions to shed some light in the constraint of geometry. So X-space doing great in soft X-rays, and we may benefit from other X-ray polarimetry missions in harder energy rates. Thank you very much.
Okay. Thank you so much, Luis. Any questions for Luis in the audience? Sorry, yeah.
Thank you. You go back to the long-term light curve that you showed a few times on that. Yeah, which this one is fine now. So I was wondering, whenever you have a little more high cadence observations, for instance, between 2017 and 18, there seems to be some shorter-term variability, around 58,000 in MJD2C in the software. Yeah, how would it fit into the picture of a processing funnel? Like, what would that be caused from?
So we discussed this short-term variability in the paper, and we say that it is something coming like a plasma coming, ionized plasma coming in the line of sight. Because also what we don't observe in the off state is a variation of NH, because it's neutral absorption. So we expect the plasma to be highly ionized, and this short-term variability, we discussed that it might be some highly ionized plasma coming into the line of sight. You see also this short-term variability in here, and this increasing trend. We have these two data points in NuStar. Also, we investigated, and it's exactly at this peak where we have the swift monitoring data going down with this short-term variability. So that might be one of the explanations.
Okay, thank you.
Any other questions for Luis online or in the room? So while people are thinking, I have a question on the magnetic field, because Roberta told us that for most of these pulsating ULXs, like to first order, you might think that a dipole prescription or description is okay, but we suspect it's probably like quadrupole. So what do the multi-part observations tell you about the magnetic field, and how does this play with this like geometry change?
So the latest estimation of the magnetic field, if I'm recalling correctly, is 1.5 to 10 to the 12 Gauss in the first 2025 paper, and it truncates the disk. It truncates the disk at the inner region of the precession disk. Doesn't really like affect that much, besides the fact that it truncates the disk in this geometrical explanation.
Okay, thank you. Please.
Yeah, well, we have on this question. The geometry of magnetic field could also affect the way that ionized plasma moves. So could that affect observations? Like as you said, like these small modifications could be because of ionized plasma. Perhaps magnetic field could change, like could affect in that sense.
Yes, no, definitely. So there is all this dynamic structure that changes, and the point here is, with current capabilities, we can only infer different possibilities, but we will need high resolution spectroscopy, for example, to test whether we are seeing like this plasma causing the short-term variability.
Thanks.
So we have time for one more question.
Is there emission on other wavelengths from this source, and do we have independent magnetic field estimates from those, on gamma rays or radio?
So for P13, I don't think so. I don't know. That's the answer. Yeah.
Okay. I'm afraid we need to move on to Gonzalo, but
Yes.
Yeah, it will be very useful for all of us to hear about high energy polarimetry. Let's thank Luis again. Oh, meanwhile, Gonzalo is setting up.
Oh, I think you're out. Okay, that's good. Are you floating?
Yeah.
Floating meeting controls. Oh,
Okay, yeah.
great.
Take it away. Thank you.
Thank you. Thanks everyone for being here. I'm very happy to be telling you about the cosmic neutrino background, why I think that this is a very important channel to understand the early universe and some fundamental things about the Big Bang. And I will also tell you how I think that we have a real chance at detecting it. And usually when I give this, sorry about that. Okay, that works. So usually when I put together cosmic neutrino background and detection in the talk, people immediately raise their eyebrows, because it has been thought for many decades that this was essentially an impossible task. And in this talk, I actually am going to be trying to convince you that I think it's possible, but there is an asterisk here. Well, first of all, I don't think any beyond the standard model physics is actually needed to detect the cosmic neutrino background. We only will be relying on lambda CDM and the standard model of particle physics, but there is an asterisk here. This will only be possible under certain astrophysical and experimental conditions. And I will be trying to describe those in details for you to make your own conclusions. For those of you that are not familiar with the cosmic neutrino background, these are neutrinos that decouple from the early universe plasma about 1 second after the Big Bang. And they do so via electroweak processes like the ones I'm showing here. You can have neutrino-antineutrino annihilation into electron-positron pairs, or you could have a scattering with the thermal electrons in the plasma. And if you compare the interaction rate from these processes with the Hubble expansion rate of the universe, you find that these particles decouple at about 1 megaelectron volt. I want to make a very important point here. This is the earliest universe particle probe that is observationally accessible to us, with the only exception perhaps of dark matter. And just for context, the CMB, which is an incredible tool to understand the universe in so many different ways, it's telling us things about 380,000 years after the Big Bang. So imagine all what we could learn if we detect particles that decouple just 1 second after it. To be fair, we have to acknowledge that we already have some indirect evidence of the existence of the cosmic neutrino background, and this comes from the cosmic microwave background observations itself and BBN. After neutrinos decouple, there is still electron and positron annihilation that hits the plasma. And we know that the entropy of each particle in equilibrium is conserved and scales with temperature Q. So if we compare after neutrino decoupling and beforehand, we find a ratio which is 11/4 in lambda CDM. And we do measure the cosmic microwave background and its temperature. So we can relate it to the temperature of the cosmic neutrino background to be at about 0.17 millielectron volts. So these are very cold neutrinos. And the number density is actually pretty high. It's about 300 particles per centimeter cube. Now, as I said, we have indirect evidence from CMB and BBN because these are sensitive to the effective number of relativistic degrees of freedom, which is compatible with 3 species at those redshifts. So then why is it important to detect the CNUV directly? You could ask me, we already have some indirect evidence from it. When I'm gonna give you 3 reasons, but if you ask me in private, I could also give you more. BBN and CMB only measure its gravitational effects via inferred energy density at 2 specific redshifts. No particle properties are being observed. There is no measurement of individual neutrinos, their thermal nature, momentum distribution, or spin. And a direct detection would also allow us to measure neutrino masses and clustering, possibly new physics in the neutrino sector, and what other things we cannot even imagine now happening in the universe just 1 second after the Big Bang. Okay, so why haven't we detected the CNUV? Let me show you here what is the landscape of neutrino fluxes on Earth across 22 orders of magnitude in energy. The cosmic neutrino background is the lower energy part that you see here, CMB, and as you can see, its flux is orders of magnitude larger than any other neutrino contributions on Earth. It's much larger than solar neutrinos, which we have detected to some accuracy, reactor neutrinos, atmospheric neutrinos, cosmogenic neutrinos, fine energy neutrinos in ice cube. So then why haven't we detected it? The reason is that the standard model is very bad at detecting low energy electroweak processes. The cross-section of neutrinos, for instance, with a proton scales quadratically with the neutrino energy. So at the energies of the cosmic neutrino background, the cross-section is like 10 to minus 60 centimeters squared. This is essentially undetectable. And the energy threshold, furthermore, that you would need in your experiment to detect this is very low. We're talking about millielectron volts. Solar neutrinos, for instance, they are detected with experiments that are sensitive to energy thresholds of kiloelectron volts or so. There is an alternative, though, which was proposed by Weinberg in the 60s. It was a very clever idea by Weinberg, as many others he had. He proposed that you could have the cosmic neutrino background being captured on a beta unstable nucleus, like tritium. The process is the one you could see here. Tritium would undergo the usual beta decay into helium, plus emitting an electron, no? And we have experiments on Earth that are sensitive to these processes, like the Catherine experiment in Germany, that is able to see the endpoint of the beta decay spectrum, and from that, placing a limit on the neutrino mass. Now, if this experiment were able to see an induced electron peak separated by 2 times the neutrino mass from the endpoint, that would be evidence of the cosmic neutrino background. This experiment does not see the peak, So it places a limit on what is the density of the cosmic neutrino background relative to the cosmological average. And that limit is 10 to the 11 times the prediction in lambda CDM. And this is, at least until a few years, it was the most stringent limit we had on the cosmic neutrino background. There are experiments that may improve these limits or even get closer to the lambda CDM value, like the Ptolemy collaboration that is proposed, and the US is actively involved in this. But the feasibility of this proposal has also recently been questioned due to Heisenberg uncertainty principle. The idea here is that the electrons at the endpoint of the beta decay spectrum, they inherit some quantum uncertainty from the recoiling nuclei in the beta decay process. And this quantum uncertainty is about 0.3 to 0.7 electron volts, which is on the edge of neutrino masses. So this physical picture may not be accurate, and this induced electron peak could be hidden at the tail, which would impede any detection. Here I'm going to propose another alternative, which is going to connect the least energetic neutrinos in the universe with the highest energy ones. And the reason I'm going to do so is by considering the unavoidable scatterings of cosmic rays with the cosmic neutrino background. This could happen in different environments in the universe. You accelerate cosmic rays to very high energies, and they will scatter with the cosmic neutrino background via processes like the ones I'm showing here. This is a standard model process. There is nothing exotic about it. We have measured these processes in the laboratory. And there would be two things happening here. One would be that you boost the cosmic neutrino background to very high energies, and the other one is that you break the ultra high energy cosmic ray into constituents that give you more neutrinos. And this flux happens at very high energies, no? Like those that can be searched with neutrino telescopes like IceCube. So when we first did this a few years ago, we just considered the galactic cosmic ray flux and one cosmic ray accelerator, TXS 056 plus 056, and we computed what would be the boosted cosmic neutrino background flux as a function of neutrino energy. And we found that this prediction was actually several orders of magnitude below other neutrino fluxes that you expect on Earth. But then we decided to see what would happen if you had an overdensity like the one Catherine constraint, which is 10 to the 11. If you do that, if you assume a cosmic neutrino background overdensity, which is 10 to the 11 times the cosmological value, you overshoot IceCube measurements and limits. So in other words, you can use IceCube as a way to constrain the cosmic neutrino background complementary to Catherine. This limit is still very bad, and there are several reasons for which we cannot expect an overdensity of cosmic neutrinos, which is 10 to the 11 times the lambda CDM expectation. The main reason is that neutrinos are fermions, and they have to obey Pauli exclusion limit. You cannot pack too many neutrinos in gravitational potentials. And you can actually, from the escape velocity of the system, estimate what is the maximum overdensity that you are allowed to have by Pauli. For instance, in supermassive black hole scales, this cannot be much larger than 10 to the 5. In galactic scales, maybe hundreds. And in cosmological scales, there is no escape velocity per se. So the limit you have is from the critical density of the universe, which is about 10 to the 4 times the cosmological average. And it also has been discussed that neutrinos, since they're massive, they can cluster gravitationally in galaxies. And there are simulations that have been done along these lines. It has been shown that for typical halo masses, this clustering is not much more than a factor of 10 relative to the cosmological average. So how do we get to prove these numbers? Well, the previous calculation I was showing you only was restricted to the Milky Way and one cosmic ray accelerator. But we know that cosmic rays are produced at different redshifts in the universe. So I'm just gonna compute what is the boosted cosmic neutrino background flux across different redshifts. There are analogous calculations in the literature that have been done, for instance, the diffuse supernova neutrino background or cosmogenic neutrinos, or several others. If you want to do this exercise, you need to do some assumptions, right? We cannot measure the ultra-high energy cosmic ray flux and composition at redshift 5. We only do so on Earth today, but we still have some understanding of what should be the cosmic ray flux at high redshifts. We believe that it should follow the star forming rate, quasar evolution function, or the gamma ray burst rates. And we also know that the spectral index cannot be much more different than something between 2.3 and 2.5, because otherwise you would not be able to reproduce Auger data after propagation on the cosmic microwave background. Still, these two factors introduce an uncertainty in your predictions, which is a bit more than a factor of 10. This is the figure of merit for the diffuse boosted cosmic neutrino background across redshift. and I'm showing many lines here. Let me guide you through them. The orange region in the upper left panel, these are measurements, actual measurements by IceCube of extragalactic neutrinos. And these lines, green and red ones that you see here, are upper limits on the ultra-high energy neutrino flux. We also have predictions for the cosmogenic neutrino background from cosmic ray interactions in the cosmic microwave background, shown in gray. And then in blue, I'm showing predictions for this boosted cosmic neutrino background from elastic scattering processes in dark blue, and also from deep inelastic scattering processes, which is actually the most relevant channel. You can see here that the prediction is not too far. It's only 4 orders of magnitude away from IceCube limits, which is 7 orders of magnitude better than the limit from Catherine or from the Milky Way galaxy that I was showing you before. You can translate this into limits on the cosmic neutrino background over density as a function of the lightest neutrino mass. We know that there are 3 neutrino mass eigenstates, and we know the mass differences among them. So a proper way to report these results is not in terms of just one neutrino mass, but let's say the lightest neutrino mass, and then do it for 2 different scenarios, which are inverted ordering or normal ordering. And this has an impact on the limits, especially when for very lightest neutrino masses. But the key message in this slide is that for some plausible configurations, for instance, cosmic rays that follow the quasar evolution function, the limits that you place with IceCube are below the cosmological average limit. So you are starting to prove physically meaningful values of the cosmic neutrino over density. And you could get to values between order 1 to 10 with IceCube Gen 2, which is very exciting. Is there a way to even improve this more? Well, we know that IceCube Gen 2 is not the only proposed high-energy neutrino telescopes. There are several others. Some of them are in an advanced stage, already deploying even detectors. Others are in an intermediate stage of funding process, and others I don't think will get funded. But there are certainly about 10 to 15 proposals for high-energy neutrino telescopes in the community. So we can speculate with what would be the limit if all of these experiments take place. And we found that in the most optimistic situation that cosmic rays are produced by quasars and that all these high-energy neutrino telescopes get funded, you would be able to test the lambda CDM predicted CNUV density for neutrinos that are on the high mass end, for a lightest neutrino mass larger than 0.1 electron volts, which is allowed by current data. Okay, so let's speculate even more. Imagine this happens and some of these experiments are seeing some neutrino events. It's going to be only a few of them. Is this enough to claim a detection? No, obviously no, because there are also backgrounds. The main background is the cosmogenic neutrinos from the GCK tail. You could have cosmic ray interactions with the cosmic microwave background and the extragalactic background light that produces neutrinos through these delta resonance decays. And in principle, this flux is larger than the boosted CNUP because the photopion cross-section is larger than the neutrino proton cross-section, and the number densities are similar. But there is an important point here, which is the inelasticity of the 2 processes are different. For a GCK neutrino, this typically has about 5% of the cosmic ray energy, but for the boosted CNUP, it can get up to 50%. And this is important because the cosmic ray flux falls very steeply with energy. So I think there are 2 possible ways in which you could imagine this distinction is possible. One of them is, if you look at the cosmogenic neutrino flux predictions, there is usually a bump from the transition from the extragalactic background light to the CMB. In the boosted CNUV, you do not have this bump. It's just inheriting the power law from the cosmic rays. So you could look at spectral differences, but this is still going to be very hard because the boosted CNUV is something between 0.1 and 1% of the cosmogenic. So looking at spectral differences for a background which is 4 orders of magnitude larger is a very, very difficult task. I think a more promising approach is just to look at the tail. Because of the inelasticities are different, you would expect that your cosmogenic neutrino flux will shut off at earlier energies than the boosted CNUV. So your boosted CNUV will extend to higher energies, and you may be sensitive to this bump in the tail. And as you can see here, this is not too far from projected neutrino experiments, about an order of magnitude. I have to wrap it up, so I will just say here that the composition also matters, and this is something that we are currently studying. There is extensive work on the impact of heavy nuclei on the cosmogenic neutrino predictions, but not so much on the boosted CNUB. Essentially, there is nothing for the boosted CNUB. So we are starting to discuss how the heavy nuclei composition can shift these ratios, and in some cases, it can be favorable for the boosted CNUB. And more importantly, this feature is independent on the cosmic ray composition, because for heavy nuclei, you will shift both endpoints by the same amount. Something else I want to mention is something that I did with Abby here at the CfA. We were discussing in these processes, you could also produce gamma rays. You could have neutrinos interaction with the cosmic rays, which produces a charged lepton and also mesons. These mesons will decay into gamma rays, and the charged leptons will also radiate via inverse Compton. So perhaps instead of looking at the neutrino channel, you could try with the gamma rays themselves. And we noticed that the sensitivity is actually quite similar. Like if you took the diffuse gamma ray background from Fermilab and you compare it to predictions for the gamma rays from cosmic ray neutrino interactions, the ratio is about 5 orders of magnitude. So it's a bit less stringent than IceCube, but it's a complementary way in which you could perhaps detect this flux, especially if one gets tighter limits on the diffuse gamma ray background at Fermilab. With better source modeling and better source identification, you could get these limits tighter and perhaps get sensitive to the boosted CNUB. We are not there at the moment, though. Okay, I have to wrap it up. Last thing I wanted to say is that you could imagine enhancements in the cosmic neutrino background, but this would require new physics. If the cosmic neutrino background is enhanced, actually something interesting could happen, and is that they are the dark matter, because neutrinos satisfy all the properties of the cosmic of the dark matter. They are neutral, they're stable, and if they're cold and they have the right abundance, they would be the dark matter. People disregarded this decades ago for a couple of reasons. The first one is that the number density is just not enough in lambda CDM, and also neutrinos free stream on small scales. So this would have implications for structure formation. But there are other possibilities, no? You could imagine an enhanced population of the cosmic neutrino background that does not spoil big bang nucleosynthesis, recombination, and that has to respect Pauli exclusion principle. I think I have to wrap it up, so I'm going to skip the particle physics details of the model, but if you're interested, you can ask me later. I will just show the figure of merit. Imagine you have a new particle that decays into neutrinos. It's a new particle that couples predominantly to neutrinos and decays into them. Then you can parameterize the coupling to neutrinos through some constant value times the mass of the particle. There are several constraints that you see here that will impede this to be viable. If the couplings are too small, then the particle doesn't decay to neutrinos. If the couplings are too large, it thermalizes in the early universe, and then it doesn't work. But there is this window here where the decays happen in the right time to enhance the cosmic neutrino background. The main drawback is that you need this particle to be very light. It has to be very close in mass to the cosmic neutrino background, because otherwise you inject radiation, which is constrained by the cosmic microwave background. With this, I just conclude. The cosmic neutrino background gives us access to 1 second after the Big Bang. Its direct detection would be a monumental milestone for cosmology, astrophysics, and particle physics. There could be new physics changing the cosmological history of neutrinos, which also gives us perhaps a channel to the dark matter of the universe. Traditional proposals like neutrino capture searches face fundamental and technological challenges. An alternative could be a cosmic ray boosted neutrino flux across cosmological scales, and perhaps a complementary gamma ray channel. And I think a detection in the future might be possible. Thank you.
Great, thank you so much, Gonzalo, for a very clear talk. Any questions? Okay, so can you explain to us the Catherine or Katrina limits a little bit more? Like where do they come from? And like where does huge disparity come from compared to what they observe with what you have done?
Right, so Catherine is just an experiment that has huge amounts of tritium. Tritium beta decays naturally. It's an unstable particle, no? And it decays into helium and then produces neutrinos. When you look at the energy distribution of the electrons producing these decays, and you look at the endpoint, if neutrinos are massless, you have a prediction for the endpoint. If neutrinos have a mass, you have a different prediction for the endpoint. This is particle physics clean. Catherine is able to measure electrons at the endpoint. They do not see this shape, so they can only place an upper limit on the neutrino mass, right? Now this is different. The story here is that besides beta decaying, this helium could capture a neutrino that is flying around in the detector, this cosmic neutrino background. If that happens, there will be an additional electron peak, which is this electron you see here, that shows up here.
Okay.
And this is kinematically distinct from the tail. So if they saw this peak, that would be evidence of the cosmic neutrino background, but they do not see the peak. Yeah.
Thank you so much. Any final questions from the panel?
So first, thank you for a very nice talk. So let's say that we detect neutrinos from the cosmic neutrino background. I guess that if you detected a few, it's not enough to get information from the cosmic neutrino background. So, and they are very difficult to detect. So, how optimistic are you that we can detect enough so we can understand the cosmic neutrino background and get more information from this 1 second after the Big Bang?
Right. So, yes. So, the statement that I want to make here is that if you build these high-energy neutrino telescopes, you're going to see the boosted cosmic neutrino background. Now, the question you're asking is, how many neutrinos do you need to see to extract any meaningful information about the early universe? No. Well, detecting it would already be huge. Like you're seeing the Big Bang just 1 second after it. Now, there are many things you could learn from it. For instance, you could learn neutrino masses. In this plot, you see that the predictions are depending on the neutrino mass. So if you see neutrinos here, here, or here in your parameter space, that will give you information about neutrino masses, which are otherwise very hard to measure. You could see enhancements or decreases on the density, no? Like you could be seeing here or here. That would also tell you something new about the universe. But there is still a lot of theoretical work that needs to be done in terms of like how to interpret this signal and what you could learn from it. This is a very, very young field. It's a good question. I guess something else you could learn indirectly is the ultra-high energy cosmic ray evolution. This is something you could also learn with the cosmogonic neutrinos themselves, but the boosted CNUV gives you an additional handle. That's also interesting, I guess.
Okay. So unfortunately, we're out of time just before the CFA ride. Let's thank Gonzalo and both of our speakers. Thank you so much. And we'll see you next week where we have the high energy.